In this video, I'm going to introduce some theorems here to ask two common questions in math on existence and uniqueness. When you approach a system that you're trying to solve, there are two fundamental questions to ask. One, does a solution exist? And if it exists, is the solution unique? The first theorem in this section talks about uniqueness of reduced echelon form. It turns out that each matrix is row equivalent to one and only one reduced echelon matrix. And row equivalent, what that means when one matrix is row equivalent to the other, that is that you applied one of the three elementary row operations that we learned in the first section, like interchanging two rows, multiply all entries in a row by a non-zero constant, or replace one row by the sum of itself and a multiple of another. What we've been doing to get to echelon form. By the way, this theorem does not work without the reduced here. If you just had echelon form, when you take a matrix and you forward phase it, for instance, just to echelon form, there's many different matrices. It's not unique. For instance, you could just multiply one of the rows by a non-zero constant, and then you would have another matrix, for instance. Theorem 2. Theorem 2 is our existence and uniqueness theorem. And it says here that a system is consistent, that means it exists, if and only if the rightmost column of an augmented matrix is not a pivot column. That is, if and only if an echelon form, and not even reduced, just echelon form of an augmented matrix, has to be augmented, that means there's an imaginary line here, has no row in the form, so you can't have a row of zeros with another on the other side of that line. Let me go ahead and add a line there to make that clear. And that does make sense, because if we have the situation, that means that you would have an equation that doesn't make sense. You have 0x1 plus 0x2 all the way to 0xn, depending on how large your matrix is, and then equals a number. So it would be inconsistent, which means there would be no solution, would not exist. The uniqueness part of this theorem says if a system is consistent, then the solution set contains either a unique solution, right, just one solution. That happens, by the way, when there's no free variables, or an infinitely many solutions when there is at least one free variable. And here's the paragraph in the book that justifies this. Basically says what I said, but let's go ahead and read that. When a system is in echelon form and contains no equation of the form 0 equals b, with b being non-zero, that's important, every non-zero equation contains a basic variable with non-zero coefficients. So either the basic variables are completely determined, right, with no free variables, or at least one of the variables be expressed in terms of one or more free variables. So that means it exists. In the former case, there is a unique solution. In the latter case, there are an infinite number of solutions. So if it exists, then there's either one unique solution or there's not. So this is the justification to Theorem 2. Theorem 1, to see the justification there, or the proof, it's at the end of the book in the appendixes, but you need a future chapter to be able to understand that. But you can go ahead and check that out if you're interested. Okay, let's look at an example of this. Determine the existence and uniqueness of the solutions to the following system. So I'm first going to put this into an augmented matrix. Now I'm going to interchange row 1 and row 3. I'm just going to get into echelon form, so I'm going to multiply -1 times the first row and add it to the second row. So I'll put a -1 to help me out. This would be a 0. This would be a 2. The next one, -4, 4, 2, and finally -6. Rewrite the third row. Since there's already a 0 here, then I'm going to get a 1. I think it's easier to get a 1 in that second row. So I'm going to divide that second row by 2. Finally, I'm going to take -3 times the second row and add it to the third. We're going to get a 0, 0, oh, 0, lots of zeros, but okay, good. We have a 1 there, and finally this would be a 4. So a solution does exist. It is consistent. If this would have been a 0 here, it would have been inconsistent and it wouldn't exist. So it does not have this. So again, it is consistent if and only if there is no row of this form. Okay. Well, how many solutions does it have? It has an infinite number of solutions because there are some free variables. x3 and x4 are free. You can see I circled the pivots. Those are the basic variables. These are the free ones. So we can find x1, x2, and x5 in terms of x3 and x4. But we don't need to do that. The question just asked, is it unique? And I wrote here, it is not unique because there are free variables, which is the second part of that. It says there's two choices. It's unique when there's no free variables, and there's an infinite many solutions when there is at least one free variable. So this one has an infinite many solutions. Now, if we wanted to find those solutions, the general form of those solutions, that is, then we would need to do the backwards phase. We would need to get the zeros in this column first, the last column first, and then go over to the second column and get the 0 where the -9 is. You would not, it would be too much work, though it can be done, to find the general solution here. But when you're looking at that second row, for instance, x5 is 4, so that's not too bad. x3 and x4 are free. You would plug in the 4 for x5, so that one wouldn't be too bad. But this one, when you went to go find the general solution here, not only would you need to put an x, because you don't want your answer to be in terms of x5 or x2 that are not free, so you would have to plug in the answer for 5 and then the expression for the x2. So it's easier to put this in reduced echelon form. If you're interested in seeing that solution, though we are done here, I boxed this up because that's all this asked for. I just went and wrote down the reduced echelon form here. You can figure that out by yourself. Oops, though I did make a mistake. Let me check that again. Yes, I think everything is right. I got divided by 3 there. You can see there's many forms of just echelon because I could just divide the 3 there and I would have that. I could get 1 0 here. That would also be echelon. So there's many different forms, but this one is unique as our first theorem. And so we can actually find the general form now much easier. From our third row, we know that x5 equals 4. And then from our second row, x2, if you bring these over, it's 2x3 minus 2x4 minus 7. And then from our first row, we know x1, and again, solving, moving these over, that would be 2x3 minus 3x4. Oh, I have another equal sign there, sorry. Minus 24. So this would be the general solution. So let's look at exercise 15 and 16 in the book. They use the notation example 1 that we did in our first video, where the little rectangle represents any non-zero value, and the star represents any value, including 0. Suppose that each matrix represents the augmented matrix for the system of linear equations. So we have imaginary lines when we have an augmented matrix. If these were coefficient matrices, they would not have the lines there. In each case, determine if a system is consistent, and if it is consistent, so that's the existence part, if it is consistent, determine if the solution is unique. So these are visual, because we cannot have the zeros with that b, if you remember from our theorem. So this one is inconsistent, part B, where 15 does not have a non-row, doesn't have a row of zeros with a number here. And again, remember that square is a non-zero value. So that definitely means that B is inconsistent where A is consistent. You don't need to ask the question if it is inconsistent. You can just stop. But if it is consistent, we can see that this is unique because there's a non-zero value for each one of these. So there is just one answer. There's not going to be any free variables. So 15A is consistent and unique. Number 16, both of those are consistent. We don't have a row of zeros with a number. We do have a row of zeros here, but this needs to be a non-zero number for it to be inconsistent. Are they both unique? Believe it or not, 16A is unique because there's no free variables. Even though we have this row of zeros here, there is no free variables. It has a pivot here and a pivot there. There's no column that does not have a pivot. So number 16A is consistent and unique. 16B is not unique because here, this right here is a free variable. So 16B is consistent but not unique. And that's how you do number 15 and 16. Practice problems. At the end of each section, right before you get to the exercises, there's always some practice problems for you to try. And what's great about those is there's solutions, and the solutions are at the end of the exercises. And they have a complete set of solutions here. So it's always good to try these practice problems. I have one here for you. Find the general solution to this system, just so we could do the same thing, but see that it is inconsistent. So they row reduced it. Let's go ahead and do that. To row reduce it, I'm going to first get my zeros in that first column. So I'm going to take 2 times the first row, add it to the second row to get this row right here. You can see that that does work. Get the 0, you get another 0, you get the 3, the next one is a 1, and the next one is the 3. Then I'm going to erase that, and now I'm going to do the same time, do that first, the 0 in the first column of the third row. So I'm going to multiply that by a -3 to get this row. And you can see you'll get 0, 0, -3, -1, and 2. Then what I'm going to do is I'm going to use the 3 as it. I'll erase that yellow there. And I'm going to get now 1 times row 2 added to row 3 to get a 0 underneath that pivot. So essentially we're just adding them together. And we got that row of zeros. Again, there is an imaginary line that I've added here. We got a row of zeros with a non-zero number on the right side of that imaginary line. So it is inconsistent. And the solution does explain that. Right here it says it's inconsistent because its rightmost column is a pivot column. And the third row corresponds to the equation 0 equals 5. There is no need to perform any more row operations, by the way. If you were trying to solve this, it does ask for the general solution, and you can stop here and just say inconsistent because the solution does not exist. Let's try one more. Suppose you have a 4 by 7 coefficient matrix. What does that mean? It means you have a matrix with 4 rows and 7 columns, and it says coefficient. So it's only the coefficients. There is an 8th column here for the answers. If this would have said an augmented matrix, then I would have not had that line. The line would have been here. So the matrix here says the system has 4 pivots. I do not know what the 4 pivots are. I'll arbitrarily choose them here. Why not? The question is the system consistent? And the answer is yes, because we have 4 rows, each having a pivot, 4 rows, 4 pivots. There's not going to be a 0 with a number. How many solutions are there? Well, there's free variables. x2, x4, and x6 are free. So the answer is consistent with an infinite number of solutions.